So you may recall in a previous video that we talked about the position vector. And the context was this little robot or some sort of object that moves around in this two-dimensional space along some path. And then the position vector was this arrow right here, this arrow that we draw by starting at the origin, wherever the origin is, and then we draw this arrow up to the object that's moving. And voila, there's our position vector. We call it r. It's a vector because it has a magnitude, the distance from the origin, and it has a direction, right? A direction that points towards the thing we're tracking the position of. So now what I'd like to do is define the velocity vector. Now velocity is something you probably have some intuitive sense of, right? You're driving in your car, you look down at the speedometer, speed, velocity, kind of the same thing. And the speedometer tells you you're going 35 miles per hour. So speed or velocity is a measure of how fast an object is going, right? Velocity is different from speed in the sense that velocity is a vector, where speed is just a scalar. So a speed would be that 35 miles per hour. A velocity would be 35 miles per hour going directly west, right? It gives you that direction information. But in preparing you for studying engineering dynamics this semester, I'd like to define velocity more mathematically. I'll say it that way. So we are going to define in this class velocity as the time derivative of position. Maybe be more specific, time derivative of that position vector. And while we're at it, why don't I just mention one more thing? We're also going to define acceleration, and acceleration is going to be a vector, and it's going to be the time derivative of velocity. Now a question you might have, and it would be a good one, is what the heck is a derivative of a vector? Well, to see what's going on, let's go back to the scalar derivative. So here's a function f, it's a scalar function. Then the derivative of f with respect to t, evaluated at some time I'm going to call t0, is going to be the change in f divided by the change in t. So I have f at t0 plus some little delta t into the future minus f at t0. Think of that as the current time. And then we're going to take this and divide it by that change in time. And there's a limit in this process, right? We want to take the limit as delta t goes to 0, right? We don't want to look at the change in f over a really long time, but rather just something barely into the future. So this will give us an instantaneous rate of change. So when we take the derivative of a vector, let's say we take the derivative of the position vector, and let's say we evaluate it at some time t0, guess what? When you write this down, the definition looks pretty much the same. It's this difference in position vectors, and we know how to take the difference of position vectors, right? We can add vectors, we can also subtract vectors. We divide it by the delta t, right? So here's the position vector in the near future minus the position vector currently divided by the delta t, and we take the limit just like we did for scalars as delta t goes to 0. Now if r is the position vector, like we stated just a moment ago, then this derivative of r with respect to time would be our velocity vector. So what I'd like to do in this video is to construct this derivative geometrically. I want you to see how this rate of a change of a vector with respect to time produces another vector, the derivative of the vector, which we call the velocity. We'll start off with a relatively simple case in which this object moves back and forth along a straight line. Then in subsequent videos we'll consider more interesting cases where the object is going around in a circle. And then maybe we'll try a figure 8-like pattern. Alright, so here I am. I'm in this sort of web-based plotting calculator called Geogebra. And I'm showing a point that I label point A, and it's oscillating back and forth along the straight line. This is exactly the situation I told you we'd study. Yeah, so there's A going back and forth. Alright, now I'm going to introduce another point that I call point B. Do you see point B on there now? Now point B is also oscillating back and forth along the exact same line. It goes between the exact same limits. The only difference between point A and point B is a time shift. And to show this, let me slow it down to sort of regular speed again. So here they are, points A and B, and let me pause this thing right about here. So at this instant I paused it, both A and B are traveling up and to the left. Again, the difference between point A and B is that point B is 0.3 seconds ahead of point A. Right? So in 0.3 seconds, point A will be where point B is now. You get the idea? So let me get it going again. Point A and point B doing the exact same thing. The only difference is that point B is 0.3 seconds ahead of point A. In fact, I can change the amount that point B is ahead. So now the point B is a half a second ahead. Now point B is 9/100ths of a second ahead. Right? With this little delta, with this little DT slider here, I can change how far ahead in time point B is. Now, why am I constructing a point A and a point B like this? Why do I have a future A? My B is the future A, right? Why do I have a future A? Now, you will recall the definition of the derivative of the position vector. We're taking the derivative and we're evaluating at, let's say, the current time t0. In this definition, in the numerator over here, I have two position vectors. The second one here is the position vector at the current time. And this first one is the position vector at a short time into the future, right? The current time plus a little bit of delta t. This delta t is how much into the future I'm looking. And I need to take the difference between these two position vectors. So that's why I have both of those points, the current time and a little bit into the future. Okay, so here I am back in the animation. I got B and A here. A is the current time. B is that location in the near future. I'm going to have to create position vectors, right? That definition of the derivative involves position vectors. So here I am. I'm going to put the position vector of the object at the current time. That's this green arrow right here. And I've just sort of decided that my origin is going to be up here, but my origin can be really anywhere. I could put my origin down here if I wanted to, right? Let me just move it back up here because kind of up here is going to be out of the way for us. And then I need the other position vector, so let me put that one in there as well. So there's a position vector of that point or the object in the near future. I'm making that one dashed to indicate that it's, I guess, in the future. And what I'm going to need is the difference between these two vectors. Okay, so let's think about the difference. I'm going to pause it right there, and we can think about that difference. So again, this vector right here is the position at the current time. And then up here I have the position at the current time t0 plus a little bit into the future. I'll call that delta t. And remember, what I'm looking for is the difference between those two vectors. And I'll call that difference delta r. So in this expression above with the difference, I can rewrite that if I bring the position vector at the current time to the other side. In other words, r at the current time plus the delta r is equal to r at the future time. Yeah, so let's think about this. So here's r at the current time. I want to add something to it to give me r at the future time. So the thing I add to r at the current time to get to r at the future time is a vector that looks like this. This is the delta r. It's the change in the position vector over that time interval delta t. All right, we're back in the animation now, and why don't I just put in the difference vector? There it is, that purple one right there. I call it dr on the screen here, but you see it's that position vector. It's the vector going from the current location to the future location. And you can see sometimes that vector is large, sometimes it's small, sometimes it's pointing down and to the right, sometimes it's pointing up and to the left. One thing you'll notice is that difference vector, it doesn't matter where I put the origin, right? The difference vector is what it is, right? It's independent of where I put the origin. That's kind of important for what comes up really soon. Also, I'm going to freeze the animation right here. I want you to see what happens as, and maybe you can see it in your mind, what happens if we change the delta t. This is the amount in the future that we look. So if we increase the delta t, that dr gets large because I'm looking farther into the future. If I make that delta t small, right, the dr also gets small. In fact, if I make it the dt go all the way to 0.01, these two positions are almost right on top of each other, and you can't even see the dr in this picture right here. Right? You'd have to zoom in really far to see that. So you can see that the length of the dr depends upon how big of a time difference we're looking at. Right? Let me actually get this thing going, and we can see that time difference on the fly. Sometimes that dr is small because we're at the end of this point where we're sort of turning around, but sometimes it's small because dt is small. So there's the dt small, means the dr is also small, delta r is small. Right? So there's that difference. There's that dependence in there. All right, we're coming back to this definition of the derivative of position. In other words, our velocity. So far we have this change in the position vector. What we need to do next is to divide that thing by delta t. Delta t is just a scalar. So division by a scalar is like a multiplication by 1 over delta t, right? Scalar multiplication is all cool here. So I'm going to divide by the delta t, and then after I divide by the delta t, I'm going to take this limit, delta t goes to 0. We're going to make that delta t get really small. All right, here we are back in the animation. And you'll notice I have a new vector down here. Essentially, this vector right here is the same as the difference vector, the dr, the delta r. Right? You can see this purple vector right here. The blue vector is exactly the same length. It's changing in the exact same way. I've just put it down here at the origin because I kind of like it down at the origin. But in order to turn this difference vector into a velocity, one of the things I have to do, remember, is to divide by the delta t. So let's do that right now. Let me pause right here. And now I'm going to change the code in this thing a little bit. And I'm going to divide by dt, hit return. And what do you notice right away? Hold on, hit return. Look what happened when I divide by the delta t. Did you notice something? You know, before I divided by the delta t, this vector was exactly the same as the delta r, but now I divided by the delta t, and it got a lot bigger, didn't it? It's still in the same exact direction because I'm just multiplying by a scalar. But since I'm dividing by 0.39, it gets bigger. Yeah, so that's what we're seeing in here. Let me get the animation rolling again. There it is. And now what we have is the delta t, the delta r divided by the delta t. Here's that quotient that's in our definition of velocity. All right, now there's one thing left to do to actually get the velocity. I have to take the limit, right? I have to take this dt, the delta t, and let it go to 0. Remember what's going to happen if I let dt go to 0. Remember what happens to that difference vector, the purple vector here? Point A and point B come together, so the difference goes to 0. Let's do it. So I'll take the difference, and maybe I should do it when it's moving quickly. That difference is going to 0. That difference is getting really small. Point A and point B are almost on top of each other. But since I'm dividing that difference by a very small number, in this case 0.01, my delta r divided by delta t, that quotient there in the velocity, that stays big as delta t gets to 0. Right? It stays big. So this blue vector now is my true velocity. I've got the v label on it now. You can probably barely see it. But here's the velocity now. I've taken this difference in positions. I've divided that difference in positions by the change in time. And I've taken the limit as that change in time goes to 0. And here you see the actual velocity vector. Now the way I've shown the velocity vector here is a bit disjoint. It's sort of separate from the object A. So let me put it on the object. There we go. So this velocity vector and that velocity vector, they're the exact same vector, except for the one up here has its tail attached to the object that's sliding back and forth along this line. So maybe it looks a little more natural right now. And so I almost think of our work as almost done here. So looky here. Here's the velocity vector. The velocity vector has larger magnitude when it's moving fast. Here's moving fast. It's got quite a large magnitude. Right? When it starts to turn around and slow down, you notice that magnitude shrunk quite a bit. Here it goes. It's going to shrink again. Woo, as it turns around. Notice that the velocity vector is pointed in the direction of motion. And this might get a little, maybe we can slow it down to take a closer look at that. So I'm going to slow this down. So here we go. Maybe you don't have to go that slow. Here it is. So as this point is moving up closer to the upper limit, it's slowing down, slowing down, slowing down. I'm going to stop it right here. It's still moving upward and to the right. See, it's still moving upward and to the right. It's still slowing down. Right about there, the velocity went to 0. Right? Here's where it reaches its maximum point. And now if I start it up again, there it goes. And now it's moving downward again, right? So notice that this velocity vector is always pointed in the direction of motion. And its magnitude represents how fast it's moving. I've slowed the whole thing down a bit so it's not moving very fast at all. But you can see the interpretation of the velocity vector as we're moving along the straight line. That velocity vector is always pointed sort of in line with that line of motion, and it's also pointed in the direction of motion. Interesting, if I let dt get big again, so here's the dt big, so dt of 0.5, half a second, so I've gotten rid of the difference vector. Here's the velocity if I allowed for a big dt. So here's the delta r divided by delta t with the big T dt. So this is without the limit in there. Let me let it go up a little bit. And I want to show you what happens when it reaches the top over here. Let me slow it down. So it's going to reach the top pretty soon. You can see B has reached the top, and pretty soon A is going to reach the top. And notice that at this moment A is still moving upward, right? A is still moving upward and to the left. See, there it goes. Now watch, it passes B. So A and B are right on top of each other right now. So that vector is 0 because the difference is 0. But the difference is over a big amount of time. So really, A is still moving up and to the left, and B is now moving down and to the right. So watch this. I'll let it go again. Say A is moving up and to the left. See, A is still moving up and to the left, but the vector is going down and to the right. So if I don't take the limit as delta t goes to 0, then this vector is pointing in the wrong direction. Remember, A is still going up and to the left, but this vector is going down and to the right. That's why we need to take the limit as delta t goes to 0. If I take the limit as delta t goes to 0, we can see that it's actually still going up, right? If I had the big delta t, it thinks it's going down. So it's a very small delta t that has meaning in terms of a velocity. That's why we take that limit as delta t goes to 0. And there finally it's heading back down. All right, so let's wrap up with the takeaways from this lesson. First, velocity is the derivative of the position vector. It's a derivative of a vector. Second, when an object is moving in a straight line, the velocity is aligned with that line of motion. Third, the magnitude of that velocity vector denotes the speed of the object. In other words, how fast it's going. 4, the direction of the velocity vector indicates the direction of travel. Now the final takeaway is one we haven't really discussed yet, but it's It's this. For straight line motion, our vector construction, the one we just went through, it might be a bit overkill for this situation. So let me illustrate. So if I have an object that's constrained to move just along a straight line, then I can write the position vector, at least the one we just, for the motion we just saw, as something like a times sine omega t in the e hat, what I call it, e hat 1 direction, right? So a nice sinusoidal motion along that straight line. Well, the derivative of this thing is really easy to take, right? So this vector right here is just a scalar, a sine omega t, times a vector e hat 1, but e hat 1's a constant. So the derivative of this thing is just going to be a times omega, derivative of sine is cosine omega t, and then I still have the e hat 1 there. And all those, I guess maybe the first 2, 3 of those, 4 of those takeaways we had can be deduced just from this right here. Oh boy. But nonetheless, this vector construction that we just went through is valuable. Trust me, because when we start moving along curved paths, then things are going to get more complex, and this vector construction will show you the light. All right, so this ends us here, and we'll talk about acceleration next.